Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Joe Hora and Alicia Allen with us today. Hello, Joe. Hello, Alicia.
Right.
Oh, thank you.
Joe, let's start with you. What's your geolocation?
I'm located here in Cambridge, Massachusetts at the Center for Astrophysics. And
Good. Let's see. It is May 22nd of 2025 as we record this. And is spring going full bloom in the east, or are we hitting our summer months yet?
it is full-blown spring. We're in the 40s today and raining like
Lovely.
crazy. So,
Lovely, lovely. Very nice. And Alicia, how about you? What's your geolocation and how we doing on the seasons?
Yeah, I am in Flagstaff, Arizona at
Ah,
Northern Arizona University. It's actually feeling super summery. It's very green out. It's very warm. However, it's very unpredictable in the mountains, so you never know when winter might creep back up on you.
indeed, indeed. And so you are roughly about 100 miles, 120 miles from me. I'm here in Phoenix, and yeah, we are definitely hotter than Flagstaff.
For sure.
We will definitely hit the 104s today, 105. So yeah, very toasty.
Yikes.
Yikes, right. Everybody likes to run up to Flagstaff, right? From the Valley of the Sun in the summer, they head up to Flagstaff.
So
So
true. But we come down in the winter to get some of
there
that
you
warm
go. I
snow.
just like the snowbirds. Yeah, the Canadian
Yes.
snowbirds come on down. So yeah, all good. And Alicia, what do you like to do for research?
So right now I am using near infrared to characterize asteroids. I'm
Cool.
using archival Spitzer data to find diameters and albedos for near Earth objects.
Yep.
And then I'm also using James Webb to look for hydration on main belt asteroids.
Ooh, very nice. Very cool. And Joe, what do you like to do for research?
well, a lot of it is involved projects like this that dealt with IRAC data, but right now I'm involved in a new project, which is the Spherex mission,
Oh,
which was
yes.
launched earlier this year and is going to map the sky in the zero point 0.7 to 5 micron region. So.
Cool. That would be really awesome. Get those results in. And that was a wonderful intro into this very lovely article. This is an AJ article. And where is my, there we go. Um, there we go. Okay. It's open access. It's the open access era, people. You can go grab a copy for free. Go get one. Infrared fluxes and light curves of near-Earth objects, the full Spitzer sample. And Joe and Alicia, take us away.
Okay, great. We should just mention that we've done this work here with David Trilling at Northern Arizona University. Howard Smith is also here at the CFA with me, and Andrew McNeil at Bowling Green State University. Uh,
Cool.
so this, so this project, the main topic of it was using IRAC observations to get uh, mid-infrared fluxes of near-Earth objects, which were observed throughout the Spitzer mission. Um, uh, Near Earth objects, I'll just say NEOs from here on out. They're a very interesting topic. They have a lot of scientific interest because they can tell us what the early solar system was like, and uh, we're still trying to understand the source of NEOs and how they propagate through the solar system. But the other, of course, very interesting thing is these could be the objects that eventually hit the Earth and could
We
cause
hope not.
problems for us here. So, one thing we want to know is how big these things are and what kind of danger they may present to life on Earth.
Yes.
Uh, when Spitzer first launched back in 2003, there were
Mhm.
maybe about 2,500 NEOs known. Now there's almost 40,000 known. And so the number of known objects have just exploded, and
Boom. Yeah.
uh, very little characterization has taken place of these targets. They're typically found, in optical images, but it's hard to estimate the diameter of NEOs from their optical magnitudes because they could be very dark objects that appear dim, or they could be shiny objects that may look brighter than they would otherwise
Uh-huh.
for smaller objects. So um, the infrared allows us to get a better estimate of their diameter and estimate their albedo or the reflectivity of the surface.
Good. Okay.
So Spitzer ended up observing a large, well, what we thought at the time was a large number, over 2,000 NEOs throughout the mission.
Yes.
And this was mainly during the warm Spitzer phase, which was starting in about 2009 after the cryogens were expended, and then continued on until the end of the mission in 2020.
Yes.
And so this paper collects all the different measurements and tries to analyze them in a consistent way to get the best possible fluxes
Nice.
infrared out of
Very
them.
good. Okay. Very cool. Okay, I'm with you.
So I guess you could go to maybe figure 2 that shows.
Sure. Let's take a look at figure 2. And, oh, there we go. Mosaic. Track.
Yeah, so this is a typical sky mosaic constructed from these NEO observations. And the green circles indicate where the NEO was in each frame of the observation. So when we took these data, we tracked the motion of the NEO across its apparent motion across the sky. And so we took individual, snapshots, and you can just count the number of green circles here to see how many frames we had on this object.
Dozen.
And you see that the object kind of moves through the star field, and occasionally it lands very near a star or maybe on a bad pixel on the array. So
there, yep.
We have to
sort of there
look at the different images and possibly reject images that are bad due to some of these artifacts in the image, or maybe due to a background star.
How about where there's no circle, like where you might expect one if it was strictly periodic or so?
Right. Yeah. So
those,
those indicate places where the image was rejected for some reason, and
got it.
We can see in the next figure what happened there. But this sky frame was constructed out of these individual frames, and you might notice that the stars look a little bit stretched horizontally, and that's because they're a little bit smeared out as we're tracking the NEO. So the NEO will look like a point source. It's not resolved, but it would look like a point source in these images. And this sky image then can be subtracted from each of the individual frames to leave just the NEO, and that makes it easier to measure the flux.
Cool. Okay. Shall we go down to figure 3?
Yeah, go on to the next figure.
Okay, so there's our star tracks, and I'm going to zoom out so we get all of these. There we go. Okay.
Yeah, so here this shows a little postage stamp or a little cutout of the image around the NEO in each of the frames, and you can see that sometimes it falls on between pixels or in a slightly different position, and that's just due to the the slight change in motion, change in position on the array.
As it goes, yeah.
And the frames outlined in red, those are those 2 frames that were rejected in your mosaic. So,
I'm with you. Okay, got it.
Those missing green circles, and you can see that in the upper right one, there's some little source nearby that's maybe causing a problem to the lower left of the main target, and then in the lower red frame, you can see there was really some strange event. It was probably a cosmic ray hit or something.
Bang.
That happened very close to the position. So in those cases, we just reject the frame and use the other data to extract the flux and produce the light curve.
Very cool. Okay, I'm with you. All right.
Yeah. So then we can go on to let's see. How about figure
4?
Well, 4 and 5, maybe. Yeah, you can show these on one. These are just some diagnostic plots. The upper left one just shows the offset of the NEO relative to where we think it should be on the frame. And the ones on the left were rejected because they, you can tell that the position was slightly off.
Yeah.
These are, again, those 2 rejected frames. So the position of the second one doesn't look too bad, but then if you look at the plot on the right that shows the flux as a function of time,
yes,
you see that those 2 rejected points are way outside of the norm of
Yep.
the rest of the data, so they really stand out.
Yeah, very good. Very good. What we got here?
And then the figure on the lower right kind of just shows the final result. The blue points are the light curves, so the flux as a function of time of the object. The orange points are those rejected points.
Uh-huh.
And then the green and red large points there just show the photometry that we extracted from the mosaic by putting all those individual frames together.
Right.
And the green points are the mean of all the blue points. So you can see that the flux of the mosaic is about the average of all the individual blue points.
Great. Good, good. A little consistency there. Very
So
nice.
if we didn't have a light curve resolved with time and we just combined all the data together, you can see that the flux we get is sort of average of all the little blue points.
Mm-hmm.
Expect.
Much nicer to have all those data points. Actually get a light curve here.
So that was that's the basic image reduction steps. And then if you go to figure 6, you see
Let me ask, since presumably this is the last, so how many total do we NEOs do we have in this full Spitzer sample?
Somewhere around 2,200.
22. Okay. Uh-huh. Okay. Okay, good.
Yeah, figure 6 just shows the mosaic of the NEOs. As I mentioned before, these are not resolved; they're unresolved point sources, but their width here is what we'd expect for the instrument spatial resolution.
Yeah, PSF. Okay.
You can
Uh-huh.
see the images look very clean with
Yep.
no artifacts.
Yes. Beautiful. Beautiful. Okay.
So this process was done for each of the 2,200 objects.
Yeah. Mm-hmm. Uh-huh.
More or less looking at each one because they're each, they often had little
Features.
individual, strange things in the image where some frames had to be rejected or adjustments had to be made in certain circumstances. So
Mm-hmm.
it was sort of an interactive process, but we have scripts that made it a little bit easier to cycle through all the different objects.
Okay. Very cool. Nice pipeline. Okay.
Great. Well, I can talk a little bit about the next parts if
Yeah.
we feel like that's where we're at here.
Yeah.
Um,
Mhm.
First, Frank, are you able to go to that first figure or will that throw you off too much?
Of the bonus ones?
Yes.
Okay. We have bonus material, people. And I think it's vaguely related to this thing right here, right?
That's right. You got it.
Okay. So we're going to bounce out to a figure here. Hello, everyone. We will go to the figures and bang.
All right, so if we look at the figure on the right of this figure here, oh, sorry, not the right, the left. We are comparing essentially these new infrared fluxes that we've determined. So from doing all of the new photometry on
Mm-hmm.
the objects to the old flux that was published for these objects. And you can kind of see they're pretty close to that one-to-one line.
Yes.
Meaning we did pretty good before. However, there are, some clear outliers. There are some that are a little bit further from that line.
Mm-hmm.
So for those, they could be objects such as Joe was talking about with the frames that had gotten rejected. Maybe these
Yeah.
objects did not have the frames rejected when they should have, or they had frames rejected that should have been included in that photometry process.
Mhm.
So we have our comparison there of our new flux values. And we can go ahead and go back to the paper.
Very cool. Gets a little thicker through here, about
Yes, yes.
20
And
to 20,
that,
a little more width to it.
yes. So that is the optical, which I don't think we discuss in this
Okay.
paper, except for the sneak peek that it will be talked about in our next paper.
Okay, cool. Very cool. And we go back to the paper and bang. Okay.
Perfect. Okay, so can scroll down just a little bit.
Sure. We
Let's
got
see
some
here.
lovely tables in this article.
Yes. Perfect. So the kind of the really important takeaway from this work is that because Spitzer has a relatively short observing time, or the observing times are long enough, and near-Earth asteroids can have relatively short rotation periods, we were actually able to get an entire thermal rotation period for
Cool.
39 of our objects.
Very cool.
And that is down in, I don't know which figure it is, but it's down there somewhere.
Slide. So this is the table for it. Light curves of unperiod samples. There's a
The
periodictogram.
periodogram to determine the periods. Perfect. And then we just have pulled out some of our objects here and showing their periods.
Okay.
Another beautiful table.
Beautiful table. And I do want to point out that these are not the full tables, people. You can go get the full thing online. So
Correct.
this
Yes.
is not
As many
2,200
objects.
entries. Okay. And then we get our first phase plot here.
Yes.
Okay,
Yes.
let's look at that for a minute.
And this is the channel 2 flux. So a lot of the objects,
Okay.
so there were two channels that were remaining in the Spitzer worm mission. So that was the IRAC band at 3.6 microns and at 4.5 microns.
Yes.
And some of the objects had observations in both of these bands, but all of the objects had observations in the 4.5 micron
Nice.
band. So a lot of the thermal data is from that 4.5 microns.
Very nice light curve.
Yes.
Mm-hmm.
And the rotational period found 5.288.
Very good.
Yes.
Mm-hmm.
And you see what the amplitude of this curve is basically goes from a low to high of almost factor of 3. So this object is very elongated and very non-uniform.
Okay.
A round object would have almost no variation, but this is very, football shaped or whatever. So.
Then York. That's an insider joke, people. Yes, you know what that is. Okay.
You'll have to fill us in.
Figure 9. That's why it's rotating, perhaps. Okay. Figure 9. Okay, and then we go into the individual objects and probably at least the more interesting ones, not all 2,200.
Correct. Yes, you got it. That would be a very long paper.
That would be a supplement. Okay, and then lower limits on some of them.
Yes. So for some of the objects where we weren't able to capture an entire light curve period, we were able to determine the lower limit on those rotation periods.
Okay, and remind me what a FAP is.
That's the false alarm probability, the statistic that's given by the method we're using to derive the periods. So if the number is low, that means it's not likely to be a false alarm. If that number gets large, then it is more likely to be a false alarm.
A little bit larger here. Not so large there. Okay, I'm good. Frames, duration. Okay, cool.
Yes.
Okay.
Right. Lots of good stuff.
So we have periods. We have Okay.
All right, then we just are talking about some of the other objects here. And let's see, figure 10. Hold on, I need to refresh myself on this one.
Yeah, why would one force a period on that one?
Yeah, this was one where we're comparing our derived period to that which was derived by somebody else. The previous observations, that's listed here.
Therian
et al. So we came up with a much longer period. So, but we were not sampling at quite a high of a cadence. So this is just showing what happens if you analyze the data given their period. And
okay.
It's rough.
I'm with you. And we got some different colors here. We got 2 green dots.
So the colors represent different phases that were sampled. So I think in one of these figures I have the sequence, but as it goes through several periods here, and each time it loops through, it gets a different color. And some of the colors only appear in some of the
like this one only this gold only appears once.
Right. So that's just an artifact of us not sampling very frequently. And
I'm good. I'm with you.
Yeah. So that's just an attempt to explain why we come up with a different number than the previous measurements.
Right. 0.491 on that one.
But I
2000.
think in the end, uh, we can't really conclude one way or the other who's right. So I think we need more observations for this object to really pin it down.
Okay. We'll come back to that. Okay. Very good. Okay.
Perfect. All right. Joe, do you want to talk about the strengths?
Hmm.
Yeah, so the a lot of these objects are in the class of what they call rapid rotators, which
Mhm.
have very quick rotation periods,
Uh-huh.
and these types of asteroids are typically uh, if they're rotating that fast, then they need some other sort of force besides just gravity and friction to hold the object together, because if it spins too rapidly, it can fly apart into pieces.
Yep.
But you can imagine like a pile of dirt would
Right.
have a pretty low maximum rotation rate, whereas if you had a solid rock that
Uh-huh.
was held together by other forces other than just gravity, that could spin much faster without falling apart. So
Hmm. Okay. Makes sense.
uh, one of our co-authors, Andrew McNeil, did that analysis for this section of the paper, and in table 6, he estimated the minimum cohesive force
Ooh.
to hold some of these objects.
Ooh. I'm with you. Uh-huh. Uh-huh.
So
Because they're still with us. They haven't fallen apart yet.
that's right. Yeah.
Rubble piles. Mm-hmm.
So these are probably not rubble piles. These are probably
Mm-hmm.
a lot more solid bodies.
Yep. And there's the estimated pressure. Yep. Okay. I'm with you.
Okay.
You. Okay.
And I guess let's see, one other thing I guess I could just mention, we used this Lomsgargle technique, which
uh-huh.
it sort of find the periods, which is a fairly common uh, analysis technique that people
Mhm.
use in astronomy, where it's similar to a Fourier transform, but it allows to have data that is very non-uniformly sampled,
Yes.
which gives Fourier transforms a problem.
Yes.
If you go to figure 8, it just shows the example for one object.
Okay. Let's take a look at figure eight. Let's slide up 9 and 8. Oh, yes. Here we go.
So
Period.
this is one of these Lomsgargle periodograms, which is just a plot of the power at certain frequencies,
Mm-hmm.
and here it's represented as periods. So uh, where that peak is
Mm-hmm.
your indication that that is probably the true period, and there will be other peaks in these plots just on resonance of that one frequency. But
Yes.
um,
Mm-hmm. With
this
it.
this is what we get for an analysis of this object, which gave the rotational period of about a half hour in
Yeah.
this case.
Mm-hmm. And doubling is that. Boop, boop, boop. Okay. Very nice. Very clean. It's a
Yeah,
clean periodogram. Very nice.
and
Okay.
I guess if we can jump all the way down to the end of Figure 20.
20. Okay. So we'll go down in this very awesome appendix, people. You got to check this out.
It shows all, yeah, it shows all the well-determined periods, but if you go down to the bottom of
Mm-hmm.
the figure, the last 2 plots,
Mm-hmm. Getting there. 19 and 20. There we go.
yeah, so this kind of shows if you can show all 4 of these plots, it would be great.
Okay.
Uh, I just wanted to point out that this Lomsgargle technique is pretty powerful in pulling out these periods. If, for example, if you look at 2013 V05,
Okay.
you look at the plot on the left, it seems like the points are just randomly falling
Yeah.
between 40 and 160
Well,
microjanskis. Seems to be no rhyme or reason to it.
yes.
But then after you determine the true period and then plot those points on a phase curve on
Cool.
the right, you can see that they very nicely make a
That's a beautiful
nice,
one.
except for a few outliers, it's a very
Yeah.
nice uniform phase rotation curve.
Very cool. Same thing here. Not a lot of pattern in channel versus time, but turn into a flux and fold.
And this 2015 XC
Good.
object is interesting because
Yeah.
it has a complicated light curve. It's not a nice uniform sinusoidal curve.
Yeah, it looks like a secondary hump almost.
And this has been known from ground-based observations. It's been observed a number of times, and it always produces these very complex light curves. So it's probably some sort of composite object that has some tumbling action or something that's causing these non-uniform curves. So
Right. It's almost like a binary, right? There are any of these binaries, so to speak, or binaries that emerged.
yeah, it could be a close contact or a
Right.
binary.
Right.
Um,
Yeah, that is interesting. Very cool. Okay.
so
All
that
right. And that's at least part of this very awesome appendix. Ooh, look at that one.
and
Got a lot of data on that
yeah, there are
one.
some very well determined light curves in
Very
there with
nice.
very high signal noise, but uh,
Mm-hmm. Very cool. We have colors here. Why is this one different? Oh, it's just the density
yeah,
of the data, yeah?
right. So again, it's
Okay.
one on the right just shows several periods overlapping each other.
Mm-hmm. Mm-hmm. No, and those are through the three P's. Got it. Okay. Very cool. Let's see. How about diameters? Because we did start off talking about wanting to do diameters and albedos and yes.
Yeah, so this figure 12 is using previously published values using the exact same techniques that I'm going to talk about in a second for
Okay.
follow-up work. So for this plot, we were able to determine the points that kind of went above that spin barrier. So objects that are of a large enough size and spinning fast enough that we
Okay.
would expect to have that internal cohesive strength. So
Okay.
normally you would see this gap, like where the points kind of cluster around the center, around
Mm-hmm.
10. Yeah,
Yeah,
you would
about.
see kind of a gap there. And we were actually able to put a lot of points in that region,
Mm-hmm.
showing
Indeed.
that these do have that internal cohesive strength.
Cool. Okay. Very nice. Very nice. So now we got diameters. Okay. How about albedos? What do we do with albedos?
Should we move on to that?
Should we transition? Okay. So the way we're going to do this, yeah, we will transition. So let's
Okay.
save that for a minute. So, uh, beautiful paper. Beautiful paper. So Joe and Alicia, I want to thank you so much for walking us through your very awesome article. Very nice.
You're very welcome.
And you touched on it, both of you touched on it differently, in different ways. So let me go ahead and ask, and where do you think we go from here, given the published article? There was some mention of additional observations. Are we having a Spitzer too, or do we have something else going up? Just general directions. Where do you think we go from here, given the published article? And I think Alicia, will start with you.
Sounds great. Yes. So I am using all of these updated thermal flux values that Joe has been able to determine for these Spitzer objects.
Okay.
And I am using those along with optical data to determine diameters and albedos for all of these objects.
Nice. Cool.
And if you would like to show my figures,
I will.
perfect.
This is going to be an exciting future, people. Okay.
All right, so we already talked about the plot on the left. The plot on the right is going to be the new optical absolute magnitude values that I used for my upcoming paper versus the old absolute magnitude values that were used. And the reason we see more scatter on the right side than we do on the left side
Uh-huh. Very
is
good.
because we are using only one observatory. We're using Pan-STARRS optical data. Previously, it was a combination of
Oh,
all observatories to
okay.
determine that average value. So there
Okay.
wasn't necessarily consistency with different transformation
Yeah.
filters, things like that.
Right.
So we using the single observatory, we were able to really hone in on that absolute magnitude value for each object.
Very cool.
Now I can't remember which figure I said was the second one. Okay, so in order to find these
Albedos.
diameters and albedos, we are using a near-Earth asteroid thermal model. So
Yes.
this will take that observed thermal flux that Joe has found for these objects, and it will fit a model flux. And with that model flux, it will determine the diameters and the albedos.
Yes.
And we use a Monte Carlo method. So it tests a random sampling of 10,000 different diameter and albedo, or sorry, absolute magnitude and flux measurements.
Okay.
It'll take that from the uncertainties of the flux and the magnitude, but it also has a random sampling of kind of outside that uncertainty value. So we end up with 10,000 results for these objects, where we can kind of see we have a Gaussian distribution for the most part of our diameter solutions on the left there, and our albedo solutions in the middle.
More Gaussian.
And then on the right, we just kind of see how our albedo and diameter results compare to one another. So we see that when there's a smaller diameter, we have a higher albedo object.
Yes.
And when we have a larger diameter, we have a smaller albedo object.
Most curious shape there.
Yeah, we call these the banana plot.
Yeah, okay.
They definitely live up to their name.
Very good. And what did you've got some highlighted parts of the diagram here.
So those are our nominal diameter and albedo solutions, and those are simply the median of all of these random 10,000 samplings.
Perfect.
And then on the right, I have two different circles. The solid circle is that nominal solution for both. And then that hollow circle is actually a solution where we did not run the Monte Carlo. And as you can see, this one is pretty close to the Monte Carlo solution, but not all of our objects look that way. Some of them were way off. So it shows that the Monte Carlo, those 10,000 simulations, really helps to narrow down that result. And then we just have our 1 sigma and 3 sigma error bars on that solution.
Yeah. Okay. Got it.
Yes.
Yes. 1, 1, 2. When you get this published, make those lines a little darker.
Oh, yes. And a
little advice from an editor. Okay.
This one's not finished. It's like, I don't know. It's hard.
Work in progress. Work in progress. I'm the one who asked about it, so I deserve what I get.
It'll look better when you interview me for that paper.
Thank you. Thank you. Okay.
All right. So this one I just thought was interesting because we can see how that thermal flux and optical absolute magnitude inputs affect the outputs.
Okay.
So we have in the
Sorry.
No, it's okay. In the orange square, we have the flux input, and then the shaded region is just those flux uncertainties, and same with the absolute magnitude. So those were the inputs into the model. And as you can see, it's testing within that range of uncertainty, but also testing some values outside of that range of uncertainty.
Yeah.
And you can see how those affect the diameter and the albedo solutions.
Good sensitivity thing to do. Very good. Okay.
And now one of the most important things I think, and I think Joe thinks as well, is that for NEOs, we have potentially hazardous objects. So it's important to be able to characterize these objects. We need to know more about them. So if we go to the next plot, one of the things I have been able to do with these updated flux measurements and these honed in optical magnitude measurements is to look and see if for the diameter of these objects, or do we have any new potentially hazardous objects that we need to worry about?
I'm with you.
Or do we have any objects that maybe are smaller than we thought and maybe aren't PHAs anymore?
Okay.
So in the green on the top, I have 20 objects that I was able to declassify as PHAs since their nominal diameter solution is actually smaller than as defined as a PHA, so less than 0.14 kilometers. And then on the right in the green, those are objects which could have a diameter smaller than 0.14 kilometers based on their uncertainty. And then same thing for the bottom in the red. On the bottom left, those are 4 objects that are not currently classified as potentially hazardous, but according to my diameter solutions and their proximity to Earth, their MOID value, they should be classified as potentially hazardous. And then same thing on the right, there's 60 objects which could also potentially be potentially hazardous based on their uncertainties on that diameter value.
Very
So
cool.
those we will need to keep an eye on.
Indeed. Indeed. So yeah, thanks for sharing a little preprint there if you like.
Yeah, absolutely. That
So
paper should
it'll be
be,
really exciting to see those come out in the next
yeah,
year or
it should be
so.
soon.
Yeah. And Joe, you mentioned always need more data, more observations. So where do we go post Spitzer?
Well, there'll be a couple of things that really increase the number of NEOs that people will discover. One will be the Rubin telescope, which will scan the whole sky
Yep.
every night and generate terrible amounts of data. And the other
Yes. Mhm.
thing that'll happen is there's this NASA mission called NEO Surveyor,
Yep.
which will be launched in a few years, and that will be an infrared mission that will it'll be more tuned to doing NEO surveys than Spitzer was,
Yeah.
have a very wide field and be able to survey a large part of the sky and discover objects that are coming close to the Earth. So
Mhm.
those two missions will be probably what generates the most number of new objects and additional uh, infrared measurements in the future.
Very cool. That'll be very exciting to see over the next couple of years. So I wish luck on anybody working on those missions. Very cool.
Yes.
Joe, Alicia, I want to thank you so much again for walking us through your very lovely article in the near future. Thanks.
Thank you.
Thank you.
And that'll do, everyone. And I hope this made your astronomy day and your NEO day just a little bit better. And we will see you on the next one. Bye bye.